Thanks, Willem. And hello, everybody. Marliana speaking here. So today I'm going to share my project about advancing soil moisture monitoring system. So this basically my first project here with Budiman Minasni and Jose Badarian, and we got another support from Matthew Webb and Darren Quinn from Tasmania government. So this is actually my master project. So I'm very excited to share to you. So first of all, I want to share about the fact of soil moisture. So soil moisture is tiny fraction of the global water, but it's essentially very important for our lives. So it regulates it regulates all the biogeochemical process in soil, including the chemical reaction and nutrient cycle in the soils. And it also affects the plant growth and the plant nutrient absorptions, which is later will impact the crop production yield. And soil moisture is also important to notice you about the water resource management, especially if you have large farming area. It can help you to decide like how much water that you need to put in your farming area. It's about irrigation and also preventing the flooding, and soil moisture is also good indicator to give you idea about the upcoming drought that maybe happen in your area. So after we know about the importance of soil moisture, this is the common way of us measuring the soil moisture. So the very traditional way to do that is just simply sampling the soil from the field, and then you weigh between the wet condition and then dry condition, and then you have the subtract between those two conditions. So you simply have the measurement of the how much water content in your soil. And then another way to do that is using a sensor of soil moisture. So it's basically you only need to put your sensor inside the soil, and then there is a monitor that can give you the indicator like how much the soil moisture level in your soil. And the next one is if you already have the soil moisture sensor, and then you can integrate it into the field, and then you connect it into ledger system, so it can basically give you the information of the soil moisture within the within a certain periodic time. So it gives you the pattern of the soil moisture, like how much the moisture changing within a day, like for example, every 15 minutes, and then you can get all the data sets quickly. And then the last one is the most advanced way to get the soil moisture measurement is using the satellite. So currently we have like advanced technology. So we have the satellite going around our Earth measuring the soil moisture. How the satellite measure is just they put the signal into the Earth's surface, and then the satellite will calculate how much signal that transfer back into the satellite, and then they have the calculation to transform the information into the measure into the soil moisture level. So the last two the last two ways that I shared to you is a kind of like a monitoring system, which is it giving you the information of soil moisture like over the time, so have it you can have the pattern of the soil moisture over the time. The next one that I'm going to share to you is about the global soil moisture data sets. So this is just roughly the idea that the global soil moisture dataset that already available publicly, that and we can access it at any time if you want to have sort of like monitoring the soil moisture in your area. And then overall, we already have a high temporal resolution, which is at least we have the daily data of the soil moisture that we can extract from these datasets, or even they already provide for 6 hour or 3 hour lead. But when you have a look on the spatial resolution, this kind of data set probably is not really fulfilling or it's not really meeting your requirement if you want to use it in a local area. Because when we plot it into the graph between the temporal resolution and spatial resolution of the soil moisture map that you need to have to do some analysis or application, like a specific application, all the global data set will fall into the needs to do the climate forecasting or maybe the weather forecasting, but it's not really meeting the requirement for the water research management or even the agricultural productions. So many studies have tried to downscale this global soil moisture data sets using various approach. And then recent study, we have one research that already tried to downscale the SMAP data sets using the deep learning approach. So this is the research from Ignacio with you, William. Yeah. And then, so it's basically this team is trying to downscale the global SMAP dataset from 9 kilometers into 90 meters spatial resolution. Using more deep learning models, they try to predict, they successfully predict the soil moisture at multi-depths. And then they tested these models in Australian soil moisture datasets. So deep learning is actually a part of the artificial intelligence. So it's really advanced method to do the downscaling process, right? So this gives us the idea to use these downscaling models into Tasmania, because at that time, the Tasmania government is start to install several probes in Tasmania to measure the soil moisture changing, particularly in agricultural lands. So if you have a look in this map of the Tasmania, the red dots means there is a soil moisture probes that already been installed at that time, which is during 2023. The picture in the left side is sort of like the one of the monitoring system that they installed. So other than soil moisture, they also measure the wind and the weather parameters around it. So further, the Tasmania it's actually have a live monitoring for several purposes, and it is established by the Department of the Natural Resource and Environment, where the Max and Darren is in, and then it's a part of the collaboration with the University of Sydney as well. And this live monitoring is aimed to track the important weather variables and the planting parameters spatially. So in this monitoring system, all the maps is presented at 80-meter resolution, and the information, especially for the weather maps, they update it every hour. So we can call it live monitoring. So using the idea that we already have the SMAP global dataset, and then if we try to use the SMAP to monitor the soil moisture over Tasmania, we can have a look the resolution of the SMAP itself. So it's very coarse, and then we can't really see like how the changes soil moisture within one field, because probably if you have like 100 or maybe 1,000 hectares of farming area, it probably just covered by 1 or 2 pixels of the SMAP datasets. So the idea is we need to downscale this dataset into a finer resolutions, aiming into 80 meters resolution. And then we use the models, the deep learning models, to produce the multi-level of soil moisture at the same times. And then we also want to make it updated every day so that we can monitor how much the moisture level that we have across Tasmania. So we narrow down the aim to simplify everything. So the first one, we need to generate the high resolution map of soil moisture itself across Tasmania. And then once we get the soil moisture maps, we need to integrate it into the monitoring system. So first we gather the data from the soil moisture probes across Tasmania. So this is roughly distribution of the stations. So it is similar with the red dots that you saw before, but it's basically telling you about the size of the dot itself. So we only have like roughly six stations that cover the data sets of the soil moisture data that cover more than 1 year monitoring period. So it's basically only 6 out of 39 stations that have more than 1 year recording. So other than that, they only have like probably 1 month or probably in between 1 month or 1 year. So it's basically not enough if you want to apply the deep learning models into this data set. That's why we also include the Australia data sets into the model using the same reference for soil water content from the AusNet and AusFlux. We also gather the data sets for the Australian data set. And in total, we have 51,000 data for the Australian data sets covering from 2016 until April 2020. So we make this as close as similar to the one that already been tested in Tasmania before by Ignacio. So the next step is we use the model that already been tested in Australia by Ignacio, which are two different deep learning models. First one is the multi-layer perceptron approach, and then the second one we include the long short-term memory approach. So basically, we use all the variables as the input into the neural network, and then we set up the output into two values representing the soil water content for the surface layer and then the subsurface layer. And then the same thing for the long short-term memory, long short-term memory, which is we apply it first for the soil moisture map from the SMAP datasets for both layers. And then output from that, we combine it into the other input from the weather, soil, and the land use dataset, and then we put it into the neural network and set into the two values with the same architecture. And since we have the Australian dataset, so we think to do additional approach when we use it into the Tasmanian predictions. So there is one method called transfer learning. So it's basically we take a trained global model, which is here we refer to the Australian models, and then we slice several layers from the global model, and then we put it into a new model, and then we create the new model exactly having the similar architecture with the global model. And then the last step is we just like pre-train the layer that haven't been trained before with using the new local data, which is here we are using the Tasmanian data. So here I have the summary of the modeling scenario that we did. So the first one, we have the Australian model, which is we only use the Australian data set, and then we employ it into the deep learning method, the deep learning model, and then we have the Tasmanian model, which is only use the Tasmanian dataset, and then we train it. We train the deep learning model based on Tasmania dataset. We call it the Tasmanian model. And then the last one is transfer learning model. So firstly, we use the Australia datasets, and then we train it as the pre-trained model or base model. And then we squeeze some layer on it. And then we fine-tuning the model using the Tasmania datasets. And we finally have the transfer model. So we're gonna compare the performance of these three models onto the soil moisture records in Tasmania. So we can see like what is the difference. So model evaluations is by validating those three models into 39 stations in Tasmania that we have before. So for the Tasmania and transfer learning for models, we follow the leave one out cross validations. So we have one station for testing, one station for validation, and the rest for training the models. And for the Australia models, because we already done the cross validation in Australian datasets, so we only apply the models into the 39 stations in Tasmania, but we're gonna calculate all the goodness of fit statistic based on each station, so we have the same distribution to compare. So all the process has been summarized in this paper, and then just published 2 months ago, if you guys want to have a look. And this is the model performance. We compared between Australia models, Tasmania models, and then transfer models. So it's basically, it's a bit not comparable plot. I knew it because I have it in a different scale. Sorry for that. If you guys can have a look on a specific range, for example, the Australian model, the error value is actually higher than compared to the others models. And also the correlation value is lower compared to the others. So that means the Australian models performing the worst compared to the other models. So it's basically telling us that we cannot just use the existing models, even though the Australian dataset maybe included only one station in Tasmania, and then we just using those model directly into the Tasmania, because it reveals from these experiments that because the characteristic of the dataset between Australia and Tasmania is actually different. So the model from Australia cannot really capture the characteristic of the soil moisture in Tasmania. That's why it performs worse compared to the others. And then for the Tasmania models, we have improvement in error level and also the correlations, but it's still the range of the error is still high. It probably because of the overfitting of the model, because some of the station is actually have a limited data, and then we forced it into the deep learning so that we don't know in a deep learning in an algorithm when they calculate it, they really can catch all the characteristic or all the variation of the soil moisture in Tasmania or not. When we compare it to transfer model, so basically the error level is dropping quite high. Means that in Tasmania model, we have the error level around 0.1. And then when we see the transfer model, we have the error value around 0.07-ish. And we can see that the correlation itself is just slightly higher than the Tasmania model, means still good. And then, but it's really, it's already showing us that the transfer model is actually perform better compared to the Tasmanian model itself. So it can be promising if you want to specify your big model into a certain area, you better to use the transfer learning model rather than use directly, or maybe only use the local model to build one model for the one area. Based on this result, we finally choose the transfer model as our final models, and then compare the comparison between the MLT and the LSTM. We see that the LSTM can give us better result for both surface and subsurface soil moisture, which we set it to be predicted at the same time. That means this could be better as the final models. So after we finalize the models to predict the soil moisture at both surface and subsurface layer, we then apply the models into the raster file of the variables. So here we have the final product of the soil moisture maps at 80-meter resolution. So in this picture, it is the example of the soil moisture maps. For the subsurface, you can see that the agricultural area, the soil moisture is ranging from 10 to probably 30%. And then most of the area in the western part of Tasmania, they predicted to be very wet. But this is not the actual, but why I'm saying that, because our model, this is a part of the limitation of our model. So our model is basically cannot predict the variation of that around that area because we don't have any measurement on that area. So it needs to be improved, probably by adding more probes within this area. So after we success getting the soil moisture maps at 80-meter resolution, so we create a framework to display the maps on the web-based GIS. So we basically set up all the inputs into a server. So we gather the SMAP dataset and the weather maps from Google Earth Engine database. And then every day we took the data that we need from the Google Earth Engine into the computer server, and then we stack them together with the static variables, which are covering the soil, the land use map, and the elevation as well. And the stack raster, we employ the deep learning models that we derived before, and then we put it into the parallel computation to generate the predicted maps. After we got the predicted maps, we have like short script to send it into the WebGIS so that it's available in a website and then it can be accessed for everyone. So basically this workflow is automatically executed every day. And then just like a little note, if there is a delay, it's possibly because there is a delay on the input data set. So if everything is okay, so people can basically access the soil moisture map for the recent dates. So at this time, I'm gonna show you the website page. So if we can click on that. So this is the live monitoring system that Tasmania government has. So basically all the soil moisture maps is available on this link, or maybe you can
use the QR code.
Yeah, use the QR code if you want to check. Yeah. Hopefully it's available there. So basically I want to show you how detailed our map is. So this is the example of the map last year, I guess. Didn't update it. You can see that our map can differentiate between the irrigation area and then the surrounding. So that means like it is good if you have this map to monitor your farming area maybe, and then you want to calculate how much water that you want to use. But of course, we need to refine it to the better accuracy if we need to do it or to use it for the irrigation purposes. This is a cool one. I mean, I really love this map.
Yeah.
So yeah, and then another example of the application, if we have the moisture maps available for several time periods, and then it's available in the maps. That means we can monitor like one regions, and then we can see the changes of the soil wetness over the time. So this is only the example when we put weekly moisture level from late 2022 until 2023. So we can see that the soil over the Bengal Valley region is getting dry during the summer season, and then it's getting wet again during the winter season. So it can be useful if you want to do the monitoring for the drought, something like that. And this is the conclusion of our work for this one. So we developed the soil moisture mapping system for Tasmania using sensing and environmental data. And we proved that the transfer learning improved the model's ability in producing soil moisture maps. And the system is currently provide the daily maps at 80-meter resolution with a 1 day delay, which is our best performance because we need a time to produce the map and everything. And the future improvement is obviously if we get another data or maybe like additional probes covering the western part of Tasmania, we can improve the map accuracy that we have. So what is the next step after we have set everything for the soil moisture web? So currently we try to forecast the soil moisture. So we are looking at the possibility using the self-supervised learning model, and we implement it into the time series data of soil moisture. And we aim to forecast the moisture not only next day or probably next 2 days, but we're aiming for probably next 1 week or probably next 2 weeks to get there. So we use the approach that that introduced in this paper. So basically, they separate the soil moisture time series data into a context and a target, and then they use the context to learn how the pattern of the soil moisture is, and then they wish that the model that has been learned the pattern of the soil moisture within the certain context can reconstruct the moisture pattern that they choose as a target. So using this framework, we try to implement it into one side into the time series data of soil moisture from one side. So for example, in this graph, we have like 1 year monitoring, 1 year monitoring of soil moisture, and then we took one data set as a pair of the context soil moisture, the first 30 days as the context, and then we use the next 15 days as a target. So we create a data set based on those paired data, and then we create it every 1 day moving windows. So that means if we have 360 data sets, we can probably have 340-ish, 40 something data sets, something like that, if it makes sense. So based on that data sets, so we implement it, and then this is the results for the forecasting for the next 7 days. So you can see the black cross is the observation, and then the blue line is the 7-day forecast for the first graph. So you can see at the very beginning, our model cannot catch any pattern of the soil moisture, but after 1 and 2 years, our model can catch a little bit pattern of the soil moisture, but it's not really catching the extreme high of the soil moisture, which is, I don't know, it's probably we need to be, of course, we need to refine everything from this model because it's only the beginning. So when we try to have a look on the 1 day that it's evaluated as having positive R square on that period of predictions, we can see that the predictions, for example, for this date, we can see the pattern of soil moisture resulted from the forecasting can follow the actual soil moisture value and changing between those target periods. So that means it could be something promising in the future if we can refine this model and then use this to forecast the soil moisture for the next 2 weeks, so that if we have information like the soil moisture level 2 weeks in advance, so we can do all the, I don't know, applications that can prevent probably the drought or any flooding, something like that. Yeah. So this is just like a little additional.
Yeah.
So that's all from me. Thank you.